Hi, I didn't see you there. I'm just watching this film by Dustin Mackenzie on different binding agents and how that affects colour durability. It reminds me of this paper by Chalman et al., where they discuss application method and different taphonomic factors, such as heat and water, and how that affects colour durability. But what about the different coloured ochres themselves? It seems red is the most durable ochre, but let's conduct an experiment to find out. The purpose of this project is to find what colour pigments are more durable than others and compare these to other people's analyses. Archaeologists can use this experiment to help interpret rock art by considering what pigments may weather disproportionately. This can affect relative dating, which must be used when organic binders are not available in pigments for chronometric dating. And what is portrayed in the rock art can be affected by some aspects becoming invisible or changing colour. To give a bit of background, ochre colour is affected by many variables. Cook et al. Noted a chemical change in rock art in Cloncurry, Queensland, whereby a yellow-brown mineral, goethite, underwent a reaction that resulted in it becoming red hematite. They argue this chemical reaction could affect colour superposition interpretations. They conclude that the dominance of red in older rock art does not mean that was the colour originally painted. Then they hypothesise that yellow colours may only survive in low-temperature, deep caves. Other key literature includes Wesley et al., where it is explained that white, orange and yellow pigments are least durable as they do not bond to rock surfaces well, and that is why they weather disproportionately to red ochre. Chalman et al. Add to this list of variables and identify many more, such as the initial density of coloured crystals in the pigment, the thickness of the pigment layer, how the applicator distributes the pigment, the texture of the pigment, and leaching. By examining the literature, it's evident that this is an important experiment, as knowing what pigments weather disproportionately will aid in interpreting rock art. What is portrayed can be affected by changing colour through heat and chemical reactions. This experiment, however, also invites archaeologists to consider how what is portrayed may also be affected with some parts of rock art missing or altered from the way it was intended to look. I could compare and perhaps corroborate Wesley et al.'s work that argued orange and white pigments were least durable. The results may strengthen the need for archaeologists studying rock art to consider if there is any invisible rock art, and if there is, its chronological relationship to the rest of the art. One limitation with some of the works mentioned is that the data on colour is mostly qualitative. Mackenzie had trouble visually discerning whether there were differences between some experiments, and while Chalman et al. Explained why pigments were different colours and how they altered, their discussions of colour were also mostly qualitative. Chalman et al. Did use a Munsell colour chart. However, I hope to introduce a new way of comparing colours quantitatively by examining the numerical values of the colours before and after the weathering simulation. Traditionally, ochre would have been ground up using grindstones. Between handling each ochre colour, the spoon being used was washed and dried. As I'm purely testing for durability differences among colour, I'm not adding any binders. To limit variables, each of these colours is just being mixed with bottled water, and each mixture has the same 1:1 ratio. These larger squares up here are going to be the controls. A different glove was used for each colour.
Later. Later.
To obtain the numerical values for the ochre colours, I first blurred the image. I selected the colour picker tool and hovered it over each corner and the centres of each control and sample square. This gave me 5 data points for each square, which I later averaged. The colour picker function is set on the RGB model and gives a numerical value for each R, G and B. Using box plots to model the red, green and blue values from the control and sampled ochres is one way of visualizing the difference between the control and sample ochres. The box plots show clearly that the samples which have been watered are different from the control, but only slightly. The minimal difference in the red, green and blue values between the control and samples suggest that red is durable. For both the yellow and white ochres, their sample A was wet more than the 200 ml allocated for their colour. Due to this error in the experiment, samples A for the yellow and white ochres aren't included. The difference between the control and sample A is more evident for this yellow ochre. This suggests that it is less durable than the red. The difference of red, green and blue average values between the control white ochre and sample B white ochre is the largest difference between a control and sample. This suggests that this is the least durable colour as it has changed the most. Simply comparing the means between the control population's mean R value and the sample population's mean R value is a way to visualize difference. In addition to comparing the means between the controls and samples, I created analysis of variance tables. For the red ochre, the R values between the control versus sample A had a significant difference, with a p-value of less than 0.05, which means the difference is statistically significant. The p-value for the yellow ochre is definitely under 5%. This is also statistically significant. It is important to note, however, how much smaller this p-value is. The white ochre's p-value is also statistically significant. Again, it is important to note how much smaller the p-value is. Another test was performed to try to show this difference. A 2-sample t-test was conducted for each colour to see if there was a difference between the control and sample means. The control and sample A were the groups compared for the red ochre, and the controls and sample Bs for the yellow and white ochres. For the R values of the red ochre control group versus the red ochre sample A group, the t-value is a negative. This means that there is no statistically significant difference between these groups, and this supports for the red ochre being durable. For the R values of the yellow ochre control group compared to the yellow ochre sample B group, the t-value is 12.55, which suggests more of a difference exists for yellow ochre than red. Lastly, the R values for the white ochre control group versus the white ochre sample B group has a t-value of 31.65, the largest t-value and the greatest significant difference. This supports white being the least durable ochre colour. Although this experiment has not generated new results or ideas, it is imperative that hypotheses always have some scientific foundation. This quantitative analysis has confirmed the qualitative assertion that red ochre is the most durable and yellow and white less so. With the dried white ochre changing so drastically with only 200 ml of water acting on it, It strengthens the concern for using weathering as a relative dating technique. Further, it enhances the need to acknowledge invisible rock art and how subject and structural interpretations will thus be affected.